concentration calculations, we're going to be looking at solutions for the next little bit. And concentration is an expression that relates the amount of a solute to the amount of the solution that's present. So we're going to look at the three different types. One is household products. One is molar calculations, that's what we use at school. And environmental concentrations, which are very small concentrations. So household products are going to be things that you buy and have in your home. You might have them in your kitchen, you might have them in your bathroom. But basically what they are is a percent concentration. Basically, concentration is the amount of solute divided by the amount of solution times 100%. So there's three different percents. Percent volume per volume, where we have milliliters over milliliters. This is volume for volume times 100%. So these are the units. We've got weight by volume, which is grams of solute over milliliters of solution times 100%. And then we have a percent weight by weight, and that is grams of solute over grams of solution times 100%. Now, we can replace the word concentration with a lowercase c. So C is equal to your milliliters of your solute over milliliters of your solution. And the units for a percent concentration are grams and milliliters, never liters. So if you're given a question that has liters in it, you have to convert to milliliters. And to do that, you're going to multiply by 1,000. So our first example on the back of the page, what is the weight per weight concentration if you have 40 grams of sodium hydroxide in 400 milliliters of water? So your solute is the one that's there in smallest amounts. So sodium hydroxide is our solute. We've got 400 milliliters of water, but this is a weight per weight. So we have to have grams and grams. The density of water is that there's 1 gram for every 1 milliliter. So we have 400 grams of water. Okay, weight per weight. Concentration is 40 grams of solute, 400 grams of water times 100%. So this is 10% concentration weight by weight. Second example. How much acetic acid is dissolved in water if it is 2.5 liters of a 5% vinegar solution? So this is how they make vinegar. They dissolve acetic acid in some water. And typical 5% is what you buy. So we've got 5% concentration. That's our C. We've got 2.5 liters, but we need milliliters because it's a percent, so we have to multiply that by 1,000. And now we can set up our solution. In this case, it's going to be a volume per volume because we have 2 milliliters. 2 liquids, so it's going to be milliliters. So concentration is milliliters of solute, that's your acetic acid, over milliliters of solution, that's your vinegar, times 100%. So if you rearrange this, so we can isolate the acetic acid, which is the part on top, we move everything to the other side. So concentration is going to be multiplied by the milliliters of solution. If it's divided on one side, if it's divided over here, when you move it to the other side, you do the opposite math. So 100% is multiplied on this side, we move it to the other side, it's going to have to be divided. And this will solve for milliliters of solute. I'll move this up for you. So now put in our values. We've got 5% times 2,500 milliliters divided by 100%. And that will be equal to the milliliters of solute, which is our acetic acid. So this is 125 milliliters. So basically, if I take 125 milliliters of acetic acid, dissolve it up to 2.5 liters with water, it makes a 5% solution. That just deals with household products though. At school, as a chemist, you would be dealing with molar concentrations. Now, molar concentrations have the units of moles per liter, and we use a capital C to represent concentration now, and it's moles per liter, so you take small n and divide by capital V. So concentration is equal to the moles divided by the volume in liters. If you like your triangles. Now, you have to have volume in liters, so this time, to go from milliliters to liters, you will divide by 1,000. Okay, so what is the molar concentration of a solution containing 16 grams of sodium chloride in 200 milliliters of solution? So, we don't have moles, but we do have grams of sodium chloride, and we know we've got 200 milliliters of solution. So the first thing you need to do is calculate the molar mass of sodium chloride so that you can calculate moles. It's 58.44 grams per mole. And we have to change milliliters to liters. So we're going to divide by 1,000. So we have 0.200 liters. There's 3 significant digits because there's a decimal place there. All right, so formulas. N is equal to 16 grams mass divided by molar mass. Zero 0.273785 moles. Concentration, moles divided by volume. So 0.273785 moles divided by 0.2 liters equals 1.3689 moles per liter. If you go back to the initial data, 16.0 and 200 both have 3 significant digits. So our final concentration is 1.37 moles per liter. If you want to use dimensional analysis, you can. We want our units to be moles per liter. We have our molar mass, our mass, and our volume. We want to end up with moles over liters. So, invert the molar mass. We want to get rid of grams, so we're going to multiply it by 16 grams. And we want liters to be on the bottom. So 0.2 liters is like 0.2 liters over 1. So if we invert that, now our units are moles over liters. So 1 times 16 times 1 divided by 58.44 divided by 0.2, and we get 1.37 moles per liter. So you still can use dimensional analysis if you prefer it. Next example, what's the number of moles needed to make a 200 milliliters of a 0.10 mole per liter solution? So now, let's identify what we know. We want moles. We've got volume, but we have to change it to liters. And we have moles per liter, so we have concentration. So if concentration is equal to moles divided by volume, moles is concentration times volume. 0.10 moles per liter. Take 200 divided by 1,000, and we've got 0.200 liters. So we need 0.020 moles. If you were going to do dimensional analysis, you just take the concentration because moles are on top, and you're going to cancel what's on the bottom, liters. There you go. So if I wanted to make just 200 milliliters of this solution, I would just need 0.02 moles of the substance. The last type of concentration we're going to look at is the environmental concentrations. These are usually reported as parts per million or parts per billion. For instance, lead in drinking water in Canada can only be the maximum acceptable concentration, maximum acceptable concentration for lead in water is 5 parts per billion. Currently, if you go on the Niagara Region website, we are even lower than this. It's not even detectable in our drinking water at the moment. So 5 parts per billion. Now, there isn't a maximum allowable content for sodium. This one was for lead. For sodium, but basically it gets pretty gross tasting if there's more than 200 parts per million. So that's 2 plus. So the difference between parts per million and parts per billion is 1,000. Parts per billion is 1,000 times smaller than parts per million. As of November 5th, I believe that was the last published date for Niagara Falls drinking water, our sodium was 10.6 parts per million. So way below super salty and gross. Okay, so what you're going to do when you see units, parts per million, or parts per billion, you're going to change these values into something that we can use. So it depends also which units you use, depends on which information you're given. Parts per million can be rewritten as milligram per liter, or milligram per kilogram, or microgram per gram. Microgram is 1/millionth of a gram. And we don't use that one very much at all. So 10.6 parts per million would be 10.6 milligrams of sodium for every 1 liter of water. So all you do is you change the ppm to milligram per liter or milligram per kilogram. This is dealing with drinking water, so they're going to be measuring in liters. So 250 milliliters of water contains 2.2 milligrams of oxygen. What is the concentration of oxygen in ppm? So .2 milligrams of O2 in water. So our solute is oxygen, so that's going to go on top. And the bottom has to be in liters. So change 250 milliliters to liters by dividing by 1,000. And that is 8.8 milligram per liter, which is the exact same thing as 8.8 ppm, because milligram per liter is the unit for ppm. Okay, so last example. How much dissolved oxygen is there in 4 liters of water containing 300 parts per million oxygen? So 300 ppm is the same thing as 300 milligrams per liter. We have 4 liters of water. So to figure out how much dissolved oxygen there is, then we multiply by the liters, and we have 1200 milligrams of O2 to the proper number of significant digits.